Hi everyone. Today we are discussing the topic as ALU in arithmetic computer architecture. So the ALU is expanding. It can be defined as arithmetic and logical unit. So in this representation, it is used to perform the arithmetic operations like addition, subtraction, multiplication, division, and the logical operations are and or not. So in this ALU, the data can be classified as to two types. One is fixed point number, another one is floating point number. So fixed point number, we are having a positive values and negative values. Floating point number has integral part or fractional part. So in this representation, we are having these two positive, negative integers and floating point representation, both integer part and fractional part. So in this representation, we are having a two representing instruction in your address. One is big endian, another one is little endian. So in big endian, we have to perform the most significant bit as a last one. That is, the lower byte of address are used to store the more significant bytes. That is a little endian, that's opposite, that will be represent lower byte address can be used to represent least significant byte. So next one, floating point representation. So if your first -6 and 10, it is representing a unsigned number. So for example, 6, 10. If you're representing signed number, so that is negative number, -15, -24, -36. Likewise, we have to represent with symbol that is signed number. So if you are representing a leftmost value for the negative value representation. For example, if you are representing the 6 value is 0000110. So in this 8-bit representation, if you are representing the negative number, the last bit will be representing as a 1. That is, the negative number can be represented with the help of zeros and ones. If you are having a ones complement representation in fixed point representation, so what is a ones complement? If you are having a decimal value, it will be converted to the binary value. So in this binary value, all the zeros will be converted to 1 and all the 1 will be converted to 0. So that is the answer of your ones complement representation. So if you are representing two's complement, if you are having, first of all, the first step is we have to compute, we have to calculate the ones complement, and then we can add 1 in the ones complement value, that is called two's complement. So in this example, so we have to have find out the two's complement. So 11010100. For this number, we have to calculate the ones complement. Just we have to convert zeros and ones. The next one, finally, we have to add +1 to identify the two's complement. So next one, addition and subtraction operations on fixed point number. So if you are having a unsigned number, so there is no problem. Just we have to add these two values. If you are having a signed number, we have to convert the equation to calculate the form. So for example, if you are representing 4 plus 5, so this is automatically calculated 4 plus 5 value. So if you are having a 4 plus -5 means, for that -5, we have to calculate the 2's complement for -5. And then we can add these two values. Based upon the carry bit, it will be identified as a positive or negative. So first binary addition, 0 plus 0, 0, 1 plus 0, 1, 0 plus 1, 1, 1 plus 1, that is 1, 0, 1 plus 1, sorry, 1 plus 1 plus 1 equal to 1, 1. So this is a binary addition value. So next one, we are having the example of adding or addition of two numbers, that is 6 plus 7. we have to calculate the binary value for 6 and binary value for 7, and then we can calculate these two and we can identify the value as 30. So in this add, we have half adder and we have full adder. So half adder, it's a combinational circuit which performs the 2 bits addition. So in the circuit, we are having a 3-bit addition is representing a full adder. So 3-bit addition means it will be taking a previous one carry, will be adding to the next adder. So for example, this is a half adder truth table because we are having a 2 inputs, because full adder means we have a 3 input. So in this representation, normally A plus B and sum we have to calculate the carry. So 0 plus 0, 0, sum, carry also 0. 0 plus 1 means sum is 1 and carry 0. And 1 plus 0, 1, carry 0. 1 plus 1, the sum value is 0 and the carry value will be 1. So this is a block diagram of your half adder. So two input A and B. Finally, we can get sum and carry. So this is a K-map. It is used to identify the Boolean function for representing your half adder. So this is identifying the from the truth table. We have to calculate the K-map and then we can find the logical diagram. So it is used for AND gate to find out the logical diagram for half adder. So next one, full adder. So full adder, we are having a 3-bit as input. So in this representation, this is a block diagram for representing your full adder. So 2 input and Cin is also one of the another input, that is carry from the previous block diagram. And we can, from this we can calculate the sum and we can calculate the C out. So that is carry out. So this is a output for the next full adder as a input. So this is a truth table for identifying your half adder. So all the values are 0, sum also 0, carry also 0. And if you are having a 0 plus 0 plus 1, we are having a 1 is a sum and carry is a 0. Once we are getting a 1 plus 1, at the time the carry value will be 1, the sum value will be 0. If you are having 3 ones, that is 1 plus 1, at the time sum is also 1 and carry is also 1. So this is a truth table. From this truth table, we are calculating the logical diagram for your full adder. So in this, we are using a NOR gate, and it will be taking a carry in from the previous logical gate, and it will be an input for the current logical diagram, and we can get the output from the NOR gate. So this is a representation of half adder and full adder representation. Thank you.